Hello, we are a design group from Tufts University, and our senior design project was to work with a nonprofit company known as Public Lab. Public Lab is a community where you can learn how to investigate environmental concerns using inexpensive DIY techniques. So where do we come in? Public Lab came to us with the open source problem of how do you stabilize relatively small mylar balloons on a windy day using their mini balloon mapping kit. So the concept of the mini balloon mapping kit is that you have a 32-inch mylar balloon, and you could use 2 or 3 of them and tie them together, attach a camera to the tether, and then use this to do balloon mapping. However, because these balloons are relatively small and do not provide a lot of lift, on a windy day, they're very susceptible to high drag, which essentially throws the balloons down to the ground. So as you can see here in this video, we did a benchmark test with just 3 balloons tied to a tether on a windy day. And as you can see, it's flying at a very low angle. You cannot do balloon mapping with this setup. So our design approach was to investigate a so-called Magnus effect balloon design. The Magnus effect is a effect known in fluid mechanics where a flow over a rotating cylinder or ball causes a differential pressure gradient that creates a force. Depending how you orient the rotating object in a flow, it will either cause an upward force, a sideways force, or a downwards force. This can easily be seen in baseball or soccer. As a soccer ball is rotating, it utilizes the Magnus effect and curves. So in this first video, you can see our first prototype that we were able to build and bring together. It was a bit more conservative. We used more material, but the basic concept is that there's 5 fins attached to an enclosed cylinder that is filled with 3 of the 32-inch mylar balloons that are filled with helium. And then it's attached on both ends to a spar that's attached to the tether. And as you can see this video, as it goes up in the wind, it starts to rotate. And you want the design to rotate clockwise with the wind, and that creates an upward force. If it was rotating counterclockwise in the flow, it would create a downwards force. As you can see in this video, we were able to maintain a flying angle that was pretty good on a relatively windy day. So we took these results, modified our design, but we wanted to know that we were seeing a real effect and that the prototype we came up with was much better than our benchmark or our baseline. So we attached 50 grams of weight, which represents the camera, to our Magnus effect design, and no weight to 3 balloons. We tied 3 balloons to a tether and flew our Magnus effect design on the same day. And as you can see in this picture, the Magnus effect design clearly outperforms the 3 balloons. And it should be mentioned that the Magnus effect design in this picture has 50 grams of additional weight attached to it with the entire setup, while the 3 balloons have no additional weight attached to them. So we're clearly outperforming our benchmark in this video. With this, we made some final improvements and wanted to show that the Magnus effect design could lift the camera. And as you can see in this video, that the camera is attached by a string to the spar and that it can lift it on a windy day. Finally, we wanted to test our design at higher altitudes to ensure that the effect observed at lower altitudes was maintained. As you can see in this last video, the Magnus effect design still works at higher altitudes while carrying a camera, making it ideal for balloon mapping on a windy day. We are confident that the design we have produced solves the problem of flying 3 mylar balloons on a windy day by utilization of the Magnus effect. Now in the second part of this video, my teammate is going to explain the assembly process and how you can make your own Magnus effect balloon.
These are the tools you will be using for our design. The first thing you want to do is mark the center of each balloon. Then you can go fill them up at either your local flower shop or any store that has helium available. To make your life easier during assembly, tape one of the balloons onto the floor and follow by hot gluing the next two balloons on top of each other, just like you see in the picture. It's important to note that you want the valves of each balloon to be separated by 120 degrees. Once you've found the center on both ends of the setup, we can now start working on the end mounts. These are the pieces that you will need for them. To do it, you want to cut a hole in the middle of the cardboard and stick the 3/8 inch dowel in between. It's important to note that you also want to hot glue between every cardboard layer. Once you've done this, you can attach the 4 layers onto the 2 wooden dowels, as you see in the picture, and an inch from the top, you want to roll a piece of tape so you have a place where the string can stand. Once this has done, you can attach this to the balloon, like this, and wait until you begin wrapping. For wrapping the balloons, an extra pair of hands will be useful. You want one person to hold onto the balloons while the other simultaneously wraps lengthwise all 3 balloons. You want to puncture the end supports so you're able to wrap completely all the balloons, and you want to iterate over the wrapping twice. Once you've done each wrapping, you can rotate the balloons and wrap the same way to create this X shape. Once the X shape has been created, you want to wrap in between the balloons so there is no gaps between each balloon, just like this picture. To make the fins, we used trash bags. We cut out a 9 by 18 inch rectangle, folded it in half, and ironed one side to create a cone shape that will catch the air. This is the shape that we are aiming for. We want to attach the string on the upper side of the cone, and we want to cut the excess material from the bottom side. It's also very important to note, for dynamic purposes, you want to cut out a small hole towards the end of it. This actually increases drag, just like the same as a parachute. And as you can see in our picture, with the string and with the hole, it will perform much better than if it were just glued on to our design. You repeat this process for the 5 fins. When mounting, you want to evenly space them throughout the design and use double-sided tape in each appropriate area. Then you want to use the string and tape it onto the design to make sure that the wind will always catch it. Finally, for our last part, we will begin to work on the spar. You go back to the end supports and tie a loop of string that you can just slide onto the wooden dowel. It's important to note that you don't want your loop to be too big that it'll fall off from the tape, and you don't want it too small where it'll be restricting on the wooden dowel. This is an example that we made, but you can look up online an easy to do loop knot that can sustain our support. Finally, you add an extra layer of tape on the outside to securely lock in your string. Once you've done that on both sides, you attach the string to the spar on both ends. We're using here our carbon fiber spar, which you can find on any kite kit, or equally, we used wooden dowel spars that also helped. To attach it, we did a simple iteration of tying it around the spar, adding tape, and a Ziploc for extra protection. When you attach the string to both end mounts, make sure it's about 8 feet because you will want to put the spar about 6 feet away, as you see in this picture. For the spar, we used wood initially, but we realized that it was too weak, so we found a carbon fiber rod and attached the string to both ends. Then we were able to connect it into one piece into the string, as you see here, and this became our whole connection point. We put the carbon fiber rod about 6 feet away so the string wouldn't create friction on the sides of the balloons. To attach the carbon fiber spar onto the tether, we attached a string on one side of the spar and attach it to the other side of the spar to kind of create this circle. And then we were able to attach the tether onto that string to create this V shape. And that is our final design. Some tips and tricks are, it's very helpful to work with more than one person on this project. It'll definitely make your life easier and it'll make it quicker to do. Another very important thing to note is that most of the reasoning behind a lot of these design solutions was the idea that we have to minimize the weight on the balloon. That's why we decided to iron the fins, use cardboard on the end mounts, and use saran wrap for the whole setup. If you find other ways to minimize the weight on the setup, by all means, it will fly even better. And the final thing to keep in mind is that gas expands in hotter temperatures and contracts in colder temperatures. So we worked on our project in Boston during December, so filling up our balloons at room temperature wasn't enough to fly it outside because the balloons would just shrink. If this is the case, make sure to have an extra helium tank to top off the balloons. But if you do top off the balloons outside, know that bringing them inside will cause the helium to expand and potentially cause your balloons to explode. Besides that, good luck, and we hope your design works as well as ours, if not even better. Thank you for watching our video.